1997 E&M problem number 1. We have a circuit here where there's a battery. And this looks like a real battery because the current that it provides will decrease over time. Connected to a 3.3 ohm resistor, an ammeter, and then we also have a voltmeter across the terminals of the battery. And we're going to start out by considering, well, in part 2, open circuit voltage versus the in-use voltage. All right, part 1. Determine the potential difference V naught immediately after the resistance. Okay, so right there, we're going to look for the y-intercept. And if you look really closely, I have 9.25 amps. Naturally, yours might be a little bit different, but it should be a little bit more than 9 and a little bit less than 9.5. So the voltage across the resistor is going to be I naught times R. So that would be 9.25 times 3.3, and that gets me 30.5 volts. Don't forget that all numerical answers require units. All right, part 2, open circuit voltage versus in use. So if we have an actual battery is going to have some small internal resistance. So our circuit, or at least this part of the circuit, I won't bother to draw the whole thing. This battery that they have labeled here inside my dashed box is going to be modeled by an ideal part and an internal resistance. And if we measure the voltage drop across the actual battery, when it is in use, this guy is going to be the ideal part minus the current times the internal resistance. So here's our internal resistance and our ideal part. If it's in use, the current is not 0, and the voltage that we measure will be reduced. If it's not in use, then I is 0, and the voltage that we measure is equal to just the ideal part. So for part 2, it's going to be greater. Actual V reduced by internal resistance. I'm spelling that wrong. There we go. All right, part B, determine the value of K. They've given us the exponential decay model that we're going to be using. Now that we have actual data, let's see if we can get what K is. We have I naught, that's the y-intercept. K, we're going to have to figure out a time t. So how about we use 5.5 hours? And this guy is in hours, so our K is going to be measured in hours as well. So for part B, we're going to have I equals I naught e to the minus kt. We have I naught is 9.25. And at 5.5 hours, it looks like we have a current of 1 amp. So this will be 1, and then e to the minus k, and then 5.5. So we just need to do a little bit of algebra to rearrange that, and we get a k value of 0.404, and once again, we need to have this with units because it is a numerical solution, and exponentials and sine curves and logarithms all need to have pure numbers inside them. So our k value needs to have units of reciprocal time of whatever the time units are. Now the time units are in hours, so our k value will have reciprocal of that. So 1 over hours, or if you prefer, you could have hours to the -1. These mean the same things, so it doesn't really matter which way you write it. You just need to make sure that you have that in there. All right, part C. This is where we really introduce the calculus, because when we get down to part 3, we're going to be looking for total energy from the power. All right, so see part 1, power delivered at the original time. And notice they're saying to the resistor. So we're going to have I naught squared times R, and you plug in those numbers, so 9.25 squared times 3.3, and we get power delivered of, in terms of, that's nice. We don't actually have to plug in the numbers. That's great. So we just have I naught squared R. Part 2, as a function of time t. Well, our current is going to be decreasing with an exponential decay, which we have here from part B, and they even gave it to us originally. So we're going to have power as a function of time is going to be I naught squared, and then R, and then we have e to the minus kt squared. So e to the minus kt squared is going to put a 2 up there in the exponent, and that will be as a function of time. All right, now the total energy delivered until the current is reduced to 0. Now, technically the current will be reduced to 0 after a very long time, because even at 10 hours, there's still a little bit of current left. So the energy, or maybe it would be better to start out with our definition of power. Power is the energy delivered over time. So energy is going to be the integral of power, and that's power, not momentum, so we should probably make this be a capital P for all of these, dt. So what's the power? Here's our expression for power. That's why they had us do C part 2 first, so that we could just take this whole thing and plug it in there for power. And we're going to go from 0 to infinity. We'll have I naught squared R e to the minus 2kt dt. Yes, from t equal to 0, so 0, until the current is reduced to 0. Well, that's an infinite amount of time later, technically speaking. So when we integrate this guy, remember the exponential stays the same, but we divide by what's in the exponent, so minus 2k is what we divide by. So constant goes along for the ride, exponential stays the same, divide by what's in the exponent, and then we enter our limits of from 0 to infinity, and fortunately that minus sign is going to take care of itself once we plug in our limits, because we're going to be subtracting by a negative. So I naught squared R over minus 2k, and then e to the negative really big gets us 0, minus e to the 0 gets us 1. So that negative and this negative will cancel each other out, and the energy supplied through that resistor is going to be I naught squared R over 2k. And since they told us that they want the answers in terms of our givens here, the letters, this is not a numerical solution. We don't need any units.